Electricity plays a crucial role in facilitating human activities. It is the heart of the modern economy, accountable for industrial, commercial, and domestic operations. The world's demand for electricity, alongside the increase of the global population, has been rapidly growing since the 21st century. Most power-generating plants burn fossil fuels such as coal, oil, and natural gas. In 2019, fossil fuels provided nearly 63.3% of worldwide electricity. Only 36.7% is from low-carbon sources. In this global crisis, the Philippines is not an exemption. As of 2021, the country was experiencing a rising energy crisis due to its growing population and the mandated infrastructure boom. The COVID-19 pandemic also contributes to the said crisis, and for the first half of this year alone, 17 power-generating companies went offline and breached their planned outage allowances. This results in the implementation of manual load droppings to preserve power grid stability operations. As of 2019 and 2020 reports, there are still off-grid areas with over 2,319,660 households, or more than 17,000 sitios across the country, with no access to electricity. These electrical and environmental crises call the need to transition to renewable and sustainable energy sources that could supply 4/5 of the world's electricity by 2050, and potentially end climate change and global warming. With that being said, the engineering, research, and development sector is now focusing on harnessing the untapped wind source through the airborne wind energy systems, or AWES. Two commonly used AWES are power kites and wind turbines. However, power kites are more economical than wind turbines and can operate at higher altitudes where wind speeds and available power are greater. SkyCell's Power, a company that has a passion for wind energy, is one of the contributors in developing, designing, and manufacturing airborne wind energy systems. It is the first company in the world to develop an industrial application of power kites, harnessing untapped wind sources at altitudes of up to 400 meters. SkyCell serves as an inspiration for the young researchers and aspiring mechanical engineers to design and fabricate a renewable power generation to provide solutions to the existing problems with the integration of a linear electromagnetic induction generator. This study aimed to design and fabricate a machine with linear electromagnetic induction integrated with ram airfoil, as pioneering approach for alternative and cost-effective airborne wind energy system, to provide a preliminary design and data for potential renewable electric power production in the locality of Danbantayan, Cebu. The system has three major parts: the parafoil, the rocking arm mechanism, which consists of rocking arm, counterweight and frame, and linear electromagnetic generator comprising of magnetic coil and neodymium magnets. Moreover, part of the machine is the testing equipment for data gathering. This includes the utility box and laptop for output display. Inside of the utility box are voltage sensor, 100 kilo-ohm potentiometers, current sensor, light emitting diode, Arduino microcontroller, and battery management system. Actual prototype of the machine and its parts. Parafoil. Ground system, which consists of frame, rocking arm, utility box, and electromagnetic generator. Machine operation. The initial step of the machine operation is mainly focused on System 1, which comprises the parafoil and the tethers. Through tethers or cables, the parafoil is connected to the rocking arm beam of the machine situated at the top of the ground station or body frame. The tethers are also used for manual control operation for the rolling motion of the parafoil. In order to harness the maximum wind power in the locality, the parafoil must be launched in an open area at high altitudes to fully tap the available wind energy source in the location. Next, The rolling motion of the parafoil causes system 2, which consists of the rocking arm beam, to oscillate or move upwards and downwards. The beam is attached and supported by the ground station of the machine. And it is also connected to the generator through another pair of ropes. Another material that is also part of the second system is the counterweight, which is a magnet used as a weight and is heavy and strong enough to counter and stabilize the balancing system of the rocking arm mechanism during oscillation. Moreover, to measure the instantaneous motion of the beam, an ultrasonic sensor is used that sits at a certain distance below the rocking arm beam, just enough not to be hit when the beam moves downwards. The ultrasonic sensor sends out a sound wave at an ultrasonic frequency which travels through air and waits for it to bounce back from the flat surface attached to the back portion of the beam. The internal clock in the Arduino helps determine the time delay between transmission and receiving of the sound. Considering the travel time and speed of the sound, the distance between the ultrasonic sensor and the flat surface can be determined. With this, the instantaneous velocity of the motion can now be calculated. System 3 is mainly comprised of the linear electromagnetic generator, where the kinetic energy from the parafoil is converted into useful electrical energy. The electromagnetic generator works on the principle of electromagnetic induction. The oscillating motion causes the series of magnets inside the tube to move linearly relative to the coil tightly wound around the tube. This repetitive motion of the material results to have a changing magnetic field and magnetic flux, thereby generating a voltage in the coil. To test if there is electricity produced by the generator, a light bulb is integrated into the system that serves as a power flow indicator. The produced light indicates that there is a flow of current through it. Situated just beside the flow indicator is the utility box, which houses the main circuit of the system and testing equipment that is essential for data gathering. First, the H-bridge type rectifier converts the alternating current output of the generator into direct current output before it passes through different measuring devices. Next is the battery pack, which is a set of identical lithium-ion batteries used to store the converted direct current output. Subsequently, due to the motion of the parafoil, the power produced by the generator becomes intermittent. To compensate this, Battery Management System or BMS is established to have a continuous power and to protect the battery from possible damage. Furthermore, voltage regulator regulates the voltage to limit the potential difference to 12 volts, and also it prevents the damage within the circuit. On one hand, the ACS712 current sensor measures the current flowing through the circuit and where the output analog value is analyzed by the Arduino microcontroller. 100 kilo-ohm potentiometers are used to create a voltage divider and achieve 5 volts maximum voltage across one resistor. With this, an Arduino Uno as a voltage sensor can be used. In addition, a light-emitting diode or LED serves as the load and also a light indicator to determine if there is stored power in the battery. Lastly, the data gathered is recorded and viewed in real time through a laptop that is connected to the main circuit of the system. The parameters and data shown on the screen are time, distance, voltage, current, power, and velocity. Results of field testing and stress analysis. The results of the field testing under 5 different trials of the machine, and with the parafoil launched into the atmosphere at an altitude of 30 meters above ground level, have 11.1 watts, 8.12 watts, 11.41 watts, 11.01 watts, and 10.53 maximum electrical power outputs of each trial consecutively. Furthermore, the respective linear velocities are 377.09 cm per second, 144.26 cm per second, 314.49 cm per second, 260.28 cm per second, and 344.22 cm per second. After performing a descriptive analysis on the data gathered from the field testing, the result shows a mean of 5.47, median of 5.94, and a mode of 6.89 watts. Maximum power of 11.4 was also the range of the data with a minimum of 0.01 watts. With these, the researchers are 95% confident that the power output of the field testing is between 5.34 and 5.6 watts. The various stress analysis shows that the highest stress experienced by the machine was subjected at the meeting point of the rocking arm beam and the L-shaped bracket. The rocking arm with applied concentrated load yields a maximum stress of 1.8 MPa, which is far less than the yield strength of the rocking arm, which is 282 MPa. Overall, the materials used for the machine fabrication can withstand the maximum stress induced in each component. Recommendation: for future studies, the researchers recommend integrating an automated flight control panel that helps future researchers to have much better and more precise control for the parafoil's rolling motion. The integration of the angle of attack control mechanism will also give significant contribution to the parafoil, maximizing its capabilities to harness the available wind power. Furthermore, focusing on the machine design improvements would bring a more efficient energy conversion system from parafoil's kinetic energy into electrical power output. Lastly, future researchers are encouraged to test the machine in various locations to have different results and provide solutions to different areas, since the machine's performance differs from one area to another depending on the environment's external conditions. After the successful machine fabrication and testing, it will be proposed in different LGU units in the municipality of the Bantayan to serve its purpose as an alternative power source of the locality. But it won't end there. The researchers will continue the study to maximize the use of the machine, which includes fully automating the kite's flight maneuver and other configurations. Kite of Hope: the future of renewable power generation.